Hello everyone, this is another video, the PhD preparation video, where we'll be discussing questions that may be asked to you from statistical mechanics. Okay, if you suppose say that if they ask you what are your favorite subjects, and it's a quantum mechanics, statistical mechanics, or something like that, like statistical mechanics, if you say, then you'll be asked some questions from statistical mechanics. So these will be the questions that I'll be discussing today, that may be asked to you in an PhD interview. Okay. So first question, they will start with basics. That is, what is the difference? What is the what is the difference? Statistical mechanics. What is the difference between uh, distinguishable and indistinguishable particles? How do you distinguish between distinguishable and indistinguishable particles? That is the question. What is the difference between distinguishable and indistinguishable particles? Okay. So, so how do you first we will see the basics, like what is a distinguishable particle? What is a what is a distinguishable particle? Okay, what is a distinguishable particle? Distinguishable particles have the wave function, like particles having distinct wave functions are known as distinguishable particles. Like that means there is no overlapping of the wave function of the particles. Okay, these are the classical particles. Yeah, like uh, and they follow Maxwell-Boltzmann statistics. Okay, right, and we can trace the movement of particle throughout the trajectory. Yeah, we can also label the particles, like first one is A, second one is B. Distinguishable, you can distinguish them. Okay, we can also call them localized particles. Means particles can be localized. Okay, and their wave function can be written as like, so their wave function can be written as psi 1 2 is equal to psi a1 dot psi b2. Okay, so this is the wave function. So here the particle is in state A, particle in state A. This is particle in state B. Okay, so this is the your distinguishable particles. So let's write them. Let's write it down. So particles having particles having distinct wave function, particles having distinct wave function are known as distinguishable particles. Particles having distinct wave functions are known as distinguishable particles. There is no overlapping. There is no overlapping of wave function of particles. There is no overlapping of wave function of particles. Okay, so particles having distinct wave function are known as distinguishable particles. There is no overlapping of wave function of particles. So wave function will be really very plain, like this. Okay, like this. But there will be no overlapping. Okay, they cannot be overlapped. So this is wrong. This is not your distinguishable particles. These are your simply classical particles. These are simply your classical particles. Okay, and as they are classical particles, they don't obey anything that is quantum, like they don't obey Heisenberg uncertainty principle, don't obey Heisenberg, don't obey Heisenberg uncertainty principle. don't obey Heisenberg uncertainty principle. Okay, and um, so what is the meaning of don't obey Heisenberg uncertainty principle? That means we can determine the conjugate coordinate position, conjugate coordinates like position and momentum precisely at the same time for these particles. Okay, so let's write them. That means we can determine the conjugate coordinates, that is conjugate, we can determine the conjugate coordinates, that is what, position and momentum, position and momentum precisely at the same time, precisely at the same time. Okay, classical particles, they don't obey Heisenberg uncertainty principle. We can determine the conjugate coordinates at position and momentum precisely at the same time, right? So, and yeah, which statistics they will follow, because there's classical, but they will follow Maxwell Boltzmann statistics. So the ones you say they follow Maxwell Boltzmann statistics. So you will be asked, what is Maxwell Boltzmann statistics? Okay, so we will I will discuss that a bit later. Don't worry. Okay. Another point is we can trace the movement. We can trace the we can trace the movement of particle throughout the trajectory. Particle throughout the trajectory. Okay, and okay. Now we call them localized particles. Okay, we call them localized particles. That means particles can be localized. We can distinguish them where which one is where. Okay. Okay. So the wave function I already wrote for two particles. Wave function psi 1 2 can be written as psi a 1 into psi b 2. Okay. Yeah. Right. So next question can be asked, is a collection of electrons distinguishable or not distinguishable? Okay, so the answer is yes. A collection of electrons is distinguishable because we can trace the individual particles in the system. Then it will be system of identical and distinguishable particles. Okay, they will be called identical and distinguishable. Okay, so please write the question. Question will be: is a collection of electrons, is a collection of electrons distinguishable or not? Okay, is a collection of electrons distinguishable or not? Answer is yes, they are distinguishable, and because we can trace the individual particles in the system. Okay, and it will be called a system of identical and distinguishable particles. Okay, system of, because electrons are all identical, so identical system of identical and distinguishable particles. Okay, all right. Okay, next let's move to indistinguishable particles. Okay, what are indistinguishable particles? What are what are indistinguishable particles? Okay, so again, the opposite of distinguish, so particles having overlapped wave function, okay, are indistinguishable particles. What do you mean by overlapped wave function? What do we mean by no overlapping of wave function? Wave function means what do we mean by wave function? Wave function means just the probability of the particle to be there, right? Yeah, wave function is psi, but it doesn't signify anything. The square of psi signifies probability density. That means where the particle is, right? So the meaning of this wave function is we can simply trace the particle. right? So when there is a overlapping of wave function, that means we cannot trace the particle. So the wave function overlap, that means we cannot trace them. Okay, it's an overlapping situation, so we cannot trace them. So that's why it's called indistinguishable particle. We cannot distinguish them which one is which. Okay, so yeah, right on. Particles having overlapped wave function. Particles having overlapped wave function. Overlapped wave functions are indistinguishable particle. Overlapped wave functions are indistinguishable particles. Okay. Yeah. These are also called what? These are not classical. These are quantum particles. Okay. These are quantum particles. All right. And they follow quantum statistics. What are the quantum statistics? Fermi-Dirac statistics. Okay. Fermi-Dirac statistics. Fermi-Dirac statistics. And what is the other one? Bose-Einstein statistics. Fermi-Dirac statistics and Bose-Einstein statistics. All right. Okay. So they will obey, as they are quantum particles, they will obey Heisenberg uncertainty principle. Okay. They will obey Heisenberg uncertainty principle. Okay. So we cannot. What do you mean by obeying Heisenberg uncertainty principle? That means we cannot determine the complex. Sorry, the conjugates. Right. The conjugates, that is position and momentum, precisely at the same time. Right. And they are also called the opposite of indistinguishable. Is the meaning of distinguishable means localized. So meaning of indistinguishable will mean non-localized particles. Okay. So these are non-localized particles. Okay. Yeah. So we cannot trace these individual particles. We cannot trace. We cannot trace these individual particles. Okay. And indistinguishability is seen for identical particles. So like identical particle mean having similar physical properties. Okay. Charge, mass, volume, size, shape, etc. Okay. All right. Okay. So now the type of what are the types of indistinguishable particles? Okay. So next, types of what are the types of indistinguishable particles? Types of indistinguishable particles. What are the types? There will be two types of indistinguishable particles, right? Two types. Two types will be fermions. The one will be bosons, right? Fermions and bosons. And fermions are your Fermi particles. These are boson are Bose particles. Right? Okay. What are fermions? What are bosons? Sorry. What are fermions and what are bosons? Fermions are your spin half particles, half integral spin, half odd integral spin particles. Okay, like half, 3 by 2, 5 by 2, etc. Okay, and bosons are your what? Bosons are your integral spin. Bosons are your integral spin 0, 1, 2, 3, all that. Okay, what are fermions? Examples: neutrons. Okay, neutrons, electrons, neutrinos. The leptons. Okay, the leptons and baryons are fermions. Examples are leptons and baryons. Leptons means electron. Okay, positron, baryons, nucleons, neutron, proton. All right, neutrino. Yeah. neutrino is also there, all of that. And bosons basically mesons. Yeah, mesons are bosons. So you can give like photon. Photon is also. Then mesons, all the mesons like pions and kaons and all that. Okay, like pions, then kaons. Okay, these are your bosons. All right. So fermions obey what? Fermions obey Fermi direct statistics, and your bosons obey Bose-Einstein statistics. Okay. So the wave function for the fermionic system is what? It should be anti-symmetric wave function. Okay, anti anti-symmetric wave function, anti-symmetric wave function, and for bosons, these are symmetric wave functions. Again, what does it mean? We will see symmetric wave function. All right. Yeah. So let's see for fermions. Okay, for fermions, wave functions for fermions or fermionic system. Fermionic system of two particles. Okay, so it's indistinguishable. That means there is a overlapping of wave function of two particles. Suppose this is a wave function one A, so particle B. So psi 1 2 will be written as psi A 1 into psi B 2, right? This should be written like this. No, this is not. This is for distinguishable particles, right? This is not for indistinguishable particles. So how will we write for fermion? Fermion will write psi total 1 2. We will be writing it as, okay, see, psi a1 dot psi b2 minus, okay, psi, just interchange them, psi a2 into psi b1, right? And with a bit of normalization factor 1 by root 2, right? So this is the wave function for a fermionic system of two particles. Okay, suppose what is the, if we interchange everything, what will we get? Let's see, 1 by root 2 psi a2, we'll get this 2 psi b1 minus psi a1 into psi b2. All right. So if we interchange it, okay, we can write it also minus 1 by root 2. I just take the minus outside, so this becomes psi a1 into psi b2 minus psi a2 into psi b1. So if you see, this is the first wave function. So the second wave function, if we interchange the symbols, the wave function is like having a minus sign, right? Okay. So this is called your anti-symmetric wave function. If like, like if I'm interchanging the numbers and I'm getting it negative, so this is your what? This is your anti-symmetric wave function. Okay, so whenever we're getting a minus anti-symmetric, we know that this is a fermionic system. Okay, all right. Yeah, all right. For suppose for bosons, let's see. Let's check for bosons. So for a system of two bosons, let's check system of two bosons. Okay, so psi total will be symmetric. So psi total, let's say psi total 1 2 1 by root 2. Here we don't have a negative sign in between. We have a positive sign. Okay, plus psi a2 psi b1. Okay, so if I interchange the signs, I'll get the same thing, isn't it? Because there is no negative here. For meaning there was a negative sign. Sine a2 sine b1 plus sine um, a1 sine b2 psi b2. So see, this is not a, there is no change. So these are equal to each other, and this is symmetric wave function. Alright. So symmetric wave function in case of two bosons. symmetry wave function in case of two bosons. All right. What are interacting particles, non-interacting particles? What are interacting particles? Interacting particles are the ones which are affected by their neighbor. Okay, those are called interacting particles. And non-interacting particles are the ones which are not affected by their neighbor. So this can also be a question. Alright. Okay, what is extrinsic property of a system, intrinsic property of a system? What is extrinsic and intrinsic property of a system? So extrinsic, what is extrinsic property? Extrinsic property means what? Means property of the system depend on the size of the system proportional to size of the, if it is proportional to size of the system, it is called extrinsic property, okay, or extrinsic variable, okay, all right. And if it does not depend on the size of the system, okay, then it is what, it is simply intrinsic property, all right. Yeah. Okay, what is a macro state? What is a micro state? Macro state is a what? Simply the macroscopic variables for a system. Okay, all the macroscopic variables, like the thermodynamic variables at the system, are called the macro state of a system. And each macro state, okay, has so many micro states. Right? Micro states are defined corresponding to a particular macro state. Right. So various internal distinct arrangement of the system in a particular macro state are known as microstates. You can write this sentence. Various microstate. Various internal distinct arrangement. Various internal arrangement distinct arrangement of the system in a particular macro state. In a particular macro state are known as are known as microstates of a system. Micro state of a system. All right. Yeah. So microstate for a thermodynamic system is usually very large number. Okay. Yeah. So a system can have many macrostates, and there exists a large number of microstates corresponding to each macrostate. Each macrostate has a large number of like microstates. Okay. Here's the thing. Okay. So suppose there is a macrostate and there are microstates. Okay. Suppose for A system A, there are 30,000 microstates. For B, there are 40,000 microstates. C, there are like 1 lakh microstates. Okay, and D, there are 10,000 microstates. So, which is the most probable macrostate? The most probable macrostate will be the one having the most number of microstates. Okay, so this will be called most probable macrostate, not microstate, macrostate. Okay, yeah. So the macrostate having largest number of microstates is the most probable macrostate. Okay. Yeah. Alright. So the most probable macro state will have the largest entropy. Okay, yeah. So the equilibrium state has the largest entropy. See, the number is very high. Entropy is what? S is equal to K ln omega. Here omega is number of microstates. So the microstate very high. So the entropy will be very high. All right. Okay. So entropy is also this one. So entropy here, if you see, is a macroscopic variable. Okay. So we can say this entropy is a macroscopic variable. And what is the microscopic variable corresponding to entropy? That is your this omega. Okay, number of microstates. So this is a microscopic variable or microscopic parameter, right? Okay. Next question can be asked to you as what is Boltzmann distribution law? Okay, so let's do that. Boltzmann, what is Boltzmann distribution law? So Boltzmann distribution law, what does it tell about? It tells about average number of particle in an energy level at thermal equilibrium. Okay, it tells about average number of particles, average number of sorry, average number of particles in an energy level, average number of particles in an energy level at thermal equilibrium, at thermal equilibrium. All right. So what is the statement? Okay, let's see the statement of it. Statement is at thermal equilibrium, average number of particles in an energy level having degeneracy Gi will be given by what? Ni is proportional to Gi e to the power minus beta e. Okay. So write down at thermal equilibrium, average number of particles, average number of average number of particles in an energy level, in an energy level at thermal equilibrium. Sorry, wait a minute. Number of particle in an energy level is equal to having degeneracy, having degeneracy Gi is equal to Ni is proportional to, okay, Gi e to the power minus beta Ea. Okay, so this is your Ni. Okay, beta is what? Beta is your 1 by kT kbt, where kb is your Boltzmann constant. Okay, so suppose there are three energy levels. Suppose there are three energy levels. Okay, so first energy level Ni proportional to G1, N1 is proportional to G1 beta E1. Okay, N2 proportional to G2 e to the power minus beta E2, and N3 is proportional to G3 e to the power minus beta E3. Alright, yeah. So if we add, if we total, the total N will be summation Ni, right? So it will be Ni plus N1 plus N2 plus N3. So suppose proportionality we just remove A G1 e to the power minus beta E1 plus B G2 e to the power minus beta E2 plus C G3 e to the power minus beta E3. So this is your N. Okay. The total energy will be what? If you see total energy E will be summation I EI Ni. Okay, so this will be your total energy. So the total energy will be E1 A G1 e to the power minus beta E1 plus E2 B G2 e to the power minus beta E2 plus E3 C G3 e to the power n minus beta E3. Okay, so this is your total energy. Yeah. Okay. Okay. Do you know what is thermal de Broglie equivalent? Thermal de Broglie equivalent formula: lambda Th is equal to h by root over of 2 pi m kt. Okay. So this is the formula. What is mean free path? Mean free path lambda is equal to 1 by lambda is equal to 1 by root 2 pi n d square. Alright. Yeah. Where small n is your number density, that is n by v, total number of particles divided by volume. Yeah. Okay, now let's move to ensemble, which is very important for an interview. What are the type of ensembles and all? Okay. So ensemble is just a, what do we say, collection of large number of mental copies of the original system. Okay, that are macroscopically identical but different microscopically. So that is called a ensemble. Okay, mental copies of a large of original system. Okay. So three types of ensembles are there, like microcanonical, canonical, and grand canonical. Three types of ensembles are there. Okay, so we can say the ensembles are ways to study statistical mechanics. Okay, so from here we can say there are three ways to study the system in statistical mechanics. Okay, so ensembles are a way to study the system in statistical mechanics. Okay, a system can be studied by any ensemble. Okay, all these ensembles approach are entirely different, but the final result is same. Okay, final result is same. So generally we prefer canonical ensemble. Okay. Yeah. So before that, let's go to a bit of phase space. What is phase space? Another important concept is what is a phase space. What is a phase space? Phase space is this is a position, this is a momentum. So the whole this coordinate is called a phase space. Okay, it's a function of two this moment position and moment. Okay, phase space is again divided into two parts. First is a mu space. There is a mu space which is for single particle, and there is gamma space. Okay, this is for n particles. Okay, where n is greater than one, or yeah, this is also sum of mu spaces. Sum of mu spaces. Alright. So what is a mu space? Mu space is a phase space of a single particle only. Okay. Yeah. Alright. Okay. Now, uh, why do we study phase space? Okay. Because in phase space we realize ensemble theory. Okay, it's the connection between phase space and ensemble theory. Okay, suppose phase space there is this coordinate, this is position, this is momentum, and all these particles. These are called phase points. Okay, a single point is called a phase point or system of phase point is a system of ensemble. Alright. So a point in phase space is called phase point, or also it can be called a representative point. Alright. Yeah. And the whole thing is called the ensemble. This whole the collection of the phase points is called the ensemble. Alright. Okay. So a phase point actually evolves with time. Suppose it evolves with time. The time evolution of a phase point can be represented by a Hamiltonian equation. So we can say of a time evolution of a phase point. Okay, so q dot is equal to del h by del p, and p dot is equal to del h by del q. Alright, p dot is minus del h by del q, where h is the Hamiltonian is total energy of the system. Okay, and this q, this is p. So these are phase points, and suppose I do like this. So this is your phase space trajectory, the way the particle moves in this momentum position space. Okay, that is your phase space trajectory. Phase space trajectory. All right. Yeah. So the time evolution of a phase point represented by phase space trajectory. This is the time evolution. The way the position and momentum of the particle are evolving in time. Okay, they go forward in time. Okay. So according to Heisenberg uncertainty principle, we cannot define a phase point to be a sharp point in phase space. It's like collection of points. Okay, that's why there is this collection. We cannot exactly give the one single point. Yeah, because this is if you see the coordinates, these are momentum and position. So we cannot measure them simultaneously. There should be a element of error, right? Yeah, uncertainty. I would say element of uncertainty. Yeah. So next is the most important one. That is your different types of ensemble. Okay. So what are the types of ensemble? We'll see. Like we'll divide them a bit. Micro canonical. First is your micro canonical, canonical, and finally this one is your grand canonical. Micro canonical, canonical, and grand canonical. Okay, three types of system. Uh, so this here, what things are all the macro like N, V, E are constant here. Okay, number of particles, volume, and energy. What are constant in canonical? N, V, T. Okay, remember this one. And what are constant grand canonical? Mu, V, T. Mu is your chemical potential. Okay, yeah. Okay, walls. Let's talk about walls of here. Walls are here for walls. N is equal to constant. That means these are impenetrable walls. Okay, impenetrable walls, impenetrable walls, or impermeable walls, Im, impermeable walls, and walls of canonical are n is equal to again n is equal to constant. So impenetrable walls, impenetrable walls, or impermeable walls. Okay, impermeable walls. Right, and the final one is grand canonical. Here also n is equal to constants. Okay, so particles are changing in system. Yeah, walls are here. Walls are permeable. Okay, permeable walls, and or penetrable walls, permeable or penetrable. Okay, here we have rigid walls. We can say rigid. Okay, and here also rigid, and here yeah, it's rigid again. Okay, rigid, that means V is equal to constant means all are rigid. Okay, we can write V is equal to constant. The final point is E is equal, here E is equal to constant, the energy is equal to constant. That means the thermally non-conducting walls, they don't conduct energy. Thermally non-conducting walls. Okay, or diathermic walls, we can say diathermic walls. Okay, here T is constant. Here T is constant. That means thermally conducting walls. Okay, thermally thermally conducting walls or thermic walls. Thermic walls. Okay, and this one is V is equal to, okay. This one is T is equal to thermally again. This one is also thermally conducting walls. Okay, alright. So this is another point we can add. This is an isolated system. This is a closed system, and this is a open system. Okay. Yeah. So this is your differences. These are differences. All right. So please remember the differences. Okay. Yeah. So this much will be for this class. I'll be discussing more about statistical in the upcoming sessions. All right. Yeah. So yeah. Thank you. Thank you very much.